Hello there, Mr. Sutton here with the Pre-Cal Honors 8-4 Extra Practice Solutions on Conversion and Convergence of Power Series. On this problem, we're trying to figure out the interval of convergence and the function of x represented by this infinite geometric series here. So first we need to start by getting the initial value and the common ratio. So our initial value on this one, our a1, is going to be whatever I get when I plug in 0 for n, because n is the lower limit of summation on this problem. So if I raise all this stuff to the 0 power, that just gives me 1. And then for the common ratio, that's what I'm multiplying by over and over again. That's this term here that has the variable for the exponent. So 3x squared over 2, that whole thing is the common ratio. To get the interval of convergence, our common ratio, the absolute value of it, must be less than 1. So now we just have to solve this absolute value inequality. So we're going to basically get x by itself to start with here. I can do that by multiplying by 2 and dividing by 3. So we can say absolute value of x squared is less than 2/3. And now at this point, to get x by itself, I have to square root both sides. Now there's a couple tricky things when you do this. First off, we're not going to worry about a positive and a negative because the absolute value can't be less than a negative number, because absolute value is the smallest this could ever be is 0. So we can't say less than the square root of the negative square root of 2/3. So we're only going to have a positive branch. Also, when I square root this thing, I'm just going to simplify the radical. So initially, I end up with radical 2 over radical 3. But multiplying by radical 3 over itself, we end up with radical 6 over just plain old 3 for our final simplified fraction there. And now that I have x isolated inside the absolute value, I can set this up as a double inequality. So I can say negative radical 6 over 3 less than x less than positive radical 6 over 3. And that is my interval of convergence. To turn this into a function, I'm just going to use my infinite geometric sum formula. So that was s equals a1 over 1 minus r. So in this case, we've got a1 is 1, and r is 3x squared over 2. So here's a1 over 1 minus r in this situation. And I'm going to go ahead and simplify this fraction here. So I can treat this 1 as a 2 over 2. So this is really 1 over 2 minus 3x squared all over 2. And then if I just multiply by the reciprocal, I can rewrite this as 2 over 2 minus 3x squared. For this problem, we want interval of convergence and function of x represented by this infinite geometric series. Let's start by getting the a1 and the r values. For a1, that's what I get when I plug in the lower limit of summation, which is n equals 0 in this case. If I have 0 for my exponent here, this whole thing is just coming out to a value of 1. And now for the r value, that's what I'm multiplying by over and over again. That's just this whole negative x squared bit that's being raised to the nth power. All right, so to get the interval of convergence, I have to take my common ratio, the absolute value of this, and set this less than 1. And now solving for x here, first off, we can turn this whole thing inside here positive, because it's inside an absolute value. So absolute value is going to make negative and positive version of this thing come out the same. Next, we're going to square root both sides. Now when I do this, I don't have to write plus or minus 1, because we can't have an absolute value being less than a negative number. So we're just going to write absolute value of x is less than positive 1. And that other branch is just kind of an extraneous branch that doesn't give us anything useful. So here now, I can split this up into one of those double inequalities. So I can say that x is between negative 1 and positive 1. So negative 1 less than x less than positive 1. So that's my interval of convergence. Now for the function of x, we're just going to do a1 over 1 minus r. So that's going to be 1 over 1 minus negative x squared, which ends up actually being 1 plus x squared down there. And there's nothing else we really need to do to simplify this. To find the interval of convergence and the function of x on this geometric series, we'll start by identifying the a1 and the r values. For a1, that's what I get whenever I plug in my lower limit of summation, which is n equals 0. If I'm doing 2 times all of this stuff to the 0 power, That's really just 2 times 1. So I have an A1 value then of 2. And then for the common ratio, that's what I keep multiplying by over and over again. So for that, we look to see whatever has the variable exponent. That's this x cubed over 3 part here. All right, so for my interval of convergence, that's going to happen when the absolute value of x cubed over 3, the r value, is less than 1. So we're just going to solve for x in this absolute value inequality. So to do that, let me start by multiplying both sides by 3. So I have cube root, or actually x cubed absolute value is less than 3. And then I just have to take the cube root of both sides. So I have absolute value of x is less than the cube root of 3. And I can now turn this into one of those double inequalities. I can say negative cube root of 3 less than x less than positive cube root of 3. And that is my interval of convergence. Now to write this as a function, I can write f of x equals whatever the sum of this thing actually is. And for that, I can use my a1 over 1 minus r formula. So I can write f of x equals 2 over 1 minus x cubed over 3. And I am going to try to simplify this. So first, in the big denominator here, I'm going to do 1 minus x cubed over 3. I'm going to merge that into a single fraction. So I can think of this as 3/3 minus x cubed thirds, which is just going to be 3 minus x cubed all over 3. And now I'm just going to multiply by the reciprocal. So I've got 3 over 3 minus x cubed times 2. So that's going to be 6 over 3 minus x cubed for my final simplified answer. For this problem, I'm trying to get the interval of convergence and function of x for this geometric series. So for all of these, I'm going to start by getting my first term in my common ratio. My first term, my a1, when I plug 0 in for all of this, I'm going to get a first term of just 1, because all of this is being raised to the 0 power. So just a1 equals 1 there. For my common ratio, that's what I keep multiplying by over and over again. So every single time, because they both have a variable exponent, I'm multiplying by -1 and also x minus 4. So negative parentheses x minus 4, that whole thing is going to be my common ratio. Now for the interval of convergence, I'm going to just set my common ratio, the absolute value of this, less than 1. And then solving for x, I can really treat this all as just positive x minus 4 inside here, because it's absolute value. And then I can split that up into a double inequality. So I can write -1 less than positive whole thing here, so x minus 4 less than positive 1. And then I can just add 4 to all 3 sides to get x by itself. So I'm going to have 3 less than x less than 5. And that's my interval of convergence. Now to write this as a function, I can write f of x equals whatever the summation of all this is. And since this is an infinite geometric series, I can use my a1 over 1 minus r formula. So I can write this as f of x equals 1, the a1 value, over 1 minus this parentheses. So this is going to be actually 1 plus x minus 4 down there, because we're subtracting a negative. And then simplifying a little bit, I end up with 1 over, let's see here, this is actually going to be x minus 3 when all is said and done. For this problem, I want the first 4 terms and general term of a power series to represent this function, and then I want the interval of convergence. So let me start, since this is in infinite geometric sum form here, let me start by getting my a1 value and my common ratio. a1 is going to be whatever the numerator of all this is, which is just going to be 1. So that's the first term of my geometric series. And then for the common ratio, that's whatever I'm subtracting from 1 in the denominator. So in this case, that's positive 2x squared. So now writing out the geometric series, we have an initial term of 1, and then we're just going to keep multiplying by 2x squared to get the rest of the terms. So 1 times 2x squared is just 2x squared. 2x squared times 2x squared is 4x to the 4th. Then I have 8x to the 6th, because we're adding the exponents here. And now we have to get a general term. So we're multiplying by 2x squared a whole bunch of times. So we probably want a 2 and an x squared being raised to variables. Before I write this out, though, I have to kind of commit what I want my initial n value to be. So I'm going to commit to having an initial n value of 0. So if I want an expression that when I plug 0 into it I get 1, I'm going to have to write 2 to the n and x squared to the n, or x to the 2n. So now if I plug in 0 for n, this is really all being raised to the 0 power, giving me this initial term of 1. And then the next n value I would plug in would be 1. That would give me 2x to the 2 times 1, or 2x squared. Plugging in 2 after that would give me 4, x to the 4th, and then everything else works from there on out. Now to get the interval of convergence, I have to take my common ratio of 2x squared and set the absolute value of that less than 1. And at this point, all I have to do is solve for x. So to start that process, let me divide both sides by 2. So this is going to be a 1/2 over here. And now I'm going to take the square root of both sides. Now I'm not going to write plus or minus because you can't have absolute value being less than a negative number. So I'm just going to write absolute value of x is less than the square root, the positive root of 1/2, which if you simplify the radical, I mean you've really got 1 over radical 2, which is really multiplying by root 2 over itself. That's going to be root 2 over positive 2. That ends up simplifying 2. And then I can write this as a double-sided inequality. So negative root 2 over 2 less than x, less than positive root 2 over 2. And that is my final interval of convergence. For this problem, I want the first 4 terms in general term of a power series to represent this function, and then the interval of convergence. So to get the power function, we're basically treating this like an infinite geometric series. This is in a1 over 1 minus r form. So my a1, my first term of my series, is going to be whatever the numerator is, 3x in this case. And then for the common ratio, the r, since it's normally 1 minus r, it's going to be whatever's being subtracted from 1, so the 4x is my common ratio. To write out my series now, I start with my a1, my 3x here, and then I just keep multiplying by 4x, the common ratio, to get the rest of the terms. So 3x times 4x would be 12x squared. 12x squared times another 4x would give me my third term, which is 48x cubed. And then we have to multiply one more time by 4x to get the fourth term. So let's see here. 4 times 48. Well, 4 times 40 is 160. 4 times 8 is 32, so that's 192 overall. And then we have x to the 4th. And then we have to write that general term. All right. So when we're doing this, looking back here, we notice that we have a 3 in the very beginning. We multiply by this 3, but we only do it one time. We don't keep multiplying by 3 as we go. So this 3, since it's a one-time deal, I'm going to write 3, but I'm not going to give it any kind of variable exponent. It's just a one-shot multiplication. But now the rest of this, 4, we keep multiplying by that over and over again. So I'm going to write 4 to the nth power so that I get that repeated multiplication by 4. And now in writing it like this, I've actually kind of made a hidden decision, an implicit decision. By writing 4 to the n, I'm committing to what my very first n value is if I were to commit to any kind of starting n value. If I'm writing 4 to the n, since there's no 4 in the first term, that means the first term must have a 4 to the 0 power in it. That's why we're not seeing the 4, because it's being turned into a 1. We're multiplying by 4 0 times to get this first term. So we're committing to an initial n value of 0. This is important because I also have to write something to get this repeated multiplication by x. But now should I write x to the n or x to the n plus 1? If I write x to the n, since my first n value is implicitly 0, I'm not going to end up with this x that should be in the first term, because I'd be doing x to the 0. To get x to the 1 in the first term, I need to make this x to the n plus 1, so that when I plug in 0 for my first n value, I get x to the 1 for that first term. And now that I've done that, I'm going to get all these terms here. So if you plug in 1 for n to get this next term, you have 3 times 4 to the 1, which is 12, x to the 1 plus 1, which is 2, and the rest of these also work. Okay, so let's go to the interval of convergence now. To get that, we just take our common ratio, 4x, and set its absolute value less than 1. And very quickly here, to get x by itself, I can divide both sides by 4. I can do that while this is still inside absolute value. That's fine. So we have x less than 1/4, or I could split it up into a double inequality too. That's another way to do it. It doesn't actually matter when you do the division. So I could have done the division a step early, but I can write this as -1 less than 4x less than 1 right away, and that's also perfectly mathematically correct. So at this point then, I'll just divide by 4 to get -1/4 less than x less than 1/4. For this problem, I want first 4 terms and general term of a power series for this function. Since this is in infinite geometric series form here, this is really a1 over 1 minus r, I can use that to write out my power series. So my a1 value, my first term, is just going to be my numerator of 5. And then the common ratio that I'm multiplying by over and over again is going to be whatever's being subtracted from 1 in the denominator. Since we're doing 1 plus 5x, that means that negative 5x is my r value. All right, I'm going to use this to build my power series. My first term again is 5, so we can write f of x equals 5. And then I'm going to keep multiplying by negative 5 over x to get the rest of the terms. So 5 times negative 5x is going to be negative 25x. Multiply again by negative 5x, that's going to be positive 125x squared. And then after that, we have negative 625x cubed plus dot, dot, dot. And then we have to write the general term over here. So we're alternating between positives and negatives. So I'm going to need a -1 to the n power in my general term. Now, if I write this as -1 to the n, since my first term is supposed to be positive, that means I'm committing to an n value that's even for my first term. And I'm just going to make this n equals 0 is kind of my unspoken first n value. Now, the fact that n equals 0 is my first n value, that's going to determine how I write the exponential terms for everything else that goes into this. Because you'll notice I keep multiplying by not just -1, but also 5 and x to get the rest of these terms. So that means with my general term, I have to write 5 and x also with variables in the exponent. So I want to have a 5 to some power. But so since my first term has a 5 in it, if I was doing 5 to the 0, that wouldn't work out. I would need 5 to the 1 to get a first term of 5. So I'm going to write this as 5 to the n plus 1. That way when I plug in 0 for n, I'm actually going to get 5 to the first power instead of 5 to the 0. Next, I have an x that should also be there. So I'm also going to write x to the n plus 1. And let's see here. Actually, no, I don't want an x in the first term. Notice that we have no x in the first term. So I really do want to get x to the 0 for that first term. So I'm just going to write x to the n then. Because if I plug in 0, that just becomes a 1, and we don't see it in the first term. All right, so once you have something written out, it's good to test it out for a few n values. If we do n to the 0, this is just going to be 5 when all is said and done. If we do n equals 1, then we have -1. This is going to be 25. This is going to be x to the 1, which works out. If we plug in 2 is my next n value, now I have a positive. This becomes 125. This becomes x squared. And so all of that keeps working out. Now we have to write the interval of convergence. So for this, I take my common ratio and set its absolute value less than 1. And since I have absolute value, I can negate the whole thing inside, and it doesn't change the value of anything. And I can also divide by 5 to get x by itself. I can do that before or after I get rid of absolute value. I'm going to do it before this time around. So I'm going to write absolute value of x is less than 1/5. And then I'm just going to split this up into a double inequality. So -1/5 less than x less than positive 1/5. And that is my interval of convergence. For this problem, I want the first 4 terms and general term of a power series for this function, and along with the interval of convergence. So I'm going to treat this as an infinite geometric to write out a power series. This is essentially in a1 over 1 minus r form. So I can use that to write out an infinite geometric series that models this. My A1 value is going to just be whatever's in the numerator, so 1/3. And then for the R value, that's whatever's being subtracted from 1 in the denominator. So since it's 1 plus x over 3, that means that negative x thirds is going to be the R value. All right, so writing out my series, I have my first term of 1/3. And then I'm just going to keep multiplying by negative x over 3 to get the rest of the terms. So this is going to be, let's see here, negative x over 9. And then multiplying by negative x thirds again, I have positive x squared over 27. And then we'll have negative x cubed over, let's see, 81, 3 times 27. And that's 4 terms, so now I have to write my general term. Since we are alternating, we're going to have a negative 1 to the n power. And since my first term is positive, that means I'm committing to an initial n value of 0. So that's going to determine whether I write n or n plus 1 for everything else that goes in my general term. Other things I'm multiplying by each time. In addition to negative 1, I'm also multiplying by 1/3 because I'm dividing by 3 every single time. So I'm going to have a 1/3 to some power. Since I have a 1/3 actually in my first term, that means I want to have 1/3 to the first power for my first term. To get 1/3 to the first power, I have to write 1/3 to the n plus 1. Because again, my initial n value I said was 0, so that means I need 0 plus 1 to get that first term. And I'm also multiplying by x each time, but I don't have an x in my first term. So I want to write x to the n so that I'm doing x to the 0 for that first term. And then let's just test a few of them out. So if my first n value is 0, I've got, let's see, this is a 1, this is a 1/3, this is a 1. So we have just 1/3 positive if n is 0. If n is 1, this becomes negative. This is 1/9. This is x to the 1, so that works out. If we have if we have n equals 2, this becomes a positive again. This now is going to be 1 over 27, so that works. This is going to be x to the second, so that works. So it works if we test out the first 2 or 3. Okay, now to get the interval of convergence, I have to take my common ratio, negative x over 3, and set the absolute value of that less than 1. So a few things I can do to make my life easier. Since this is all inside absolute value, I can rewrite this as absolute value of positive x over 3. You're allowed to negate everything inside absolute value without changing the value of anything. And I can also multiply by 3 to get x by itself. And now that I've got x and just a number here, I can rewrite this as negative 3 less than x less than 3. And that is my final interval of convergence. On this problem, we want to know all values of k for which this series converges. So now let's take a look at this. This is an infinite series. All of this is being raised to the nth power, so this is an infinite geometric series because we keep multiplying by all of this over and over again. And if we want to know where a geometric series converges, that only happens when my common ratio, which is going to be all of this stuff, the absolute value of that is less than 1. So since it's geometric, we want to figure out where all of this is less than 1. And to do that, we have to essentially plug this into the calculator. This is a calculator question. So here we go. So to do this on the calculator, I'm going to enter each half of this inequality as a y equals. So I have absolute value of all this stuff first. To get that, let me do, let's see, alpha window is going to pull up my little submenu with abs in it. And now I can't use x. I'm going to use the x button in my calculator. So I've got x to the third power plus 2, and I'm going to multiply, let's say I'm going to actually need all of that in a parentheses. Let me go back and insert a parentheses back here. So let's see, there we go. And we'll put a parentheses after the 2. Great. Now we have to multiply all that by e to the negative x essentially. So e, we've got negative x. That's all inside absolute value. So I want to see basically where that's intersecting the other half of this inequality, 1. And I want to see where this first function is less than 1, is pretty much what I'm looking for. Now I need a window. It looks like if I do, say, negative 1.5 to 5, I'm going to hit all the k values that are in the answer choices. So that's how I'm picking my window. We're going to go negative 1.5, 1.5, there we go, to positive 5. And then let me do zoom, fit, zoom 0. And let's see what this looks like. Okay. So there is one function, there's the other function. So here is just kind of a picture of what all this is looking like. And you can move your window down a little bit. So let me adjust my window a little bit. Let me just go to window. And let me make my y min be, say, negative 1. So I can see just a little bit more here. Okay. So I'm trying to see where this curvy function here, which is the absolute value of my common ratio, dips below the line y equals 1. So we need to know these two intersection points because there's this little interval where the absolute value is less than 1. And it looks like we're just grazing the surface but not dipping below, so that value doesn't really matter. But over here it looks like we're crossing for just a little bit of time. So let me do second trace, and then we'll do intersect 5. And then let me go all the way back here to the first place where these things intersect. All right, so press enter 1, 2, 3 times. We have an intersection at roughly negative 1.314. And we have another intersection if I do second trace option 5 again. Let me just move a little further along. Enter, enter, enter. Negative 1.193. So between negative 1.314 and negative 1.193, that small interval is one on which this thing will converge. And now everything after whatever this intersection is will also cause us to converge. So going back to the calculator, let's do second trace one more time, option 5. And then let me move my spider all the way over here. This is going to be a long journey, but here we go. Maybe we could play some journey music while this is happening. All right, so enter, enter, enter. That's about 4.596. So for k greater than 4.596, we will also be converging for this series. So looking at my answer choices, the only one that has all of this is answer choice C.